Okay, let's look at some examples from the homework. And I want to start with number 2. This one wants me to find the definite integral of the absolute value function x minus 4. Now this is interesting because we haven't talked about antiderivative rules for absolute value functions. We don't have any. How am I supposed to calculate this area or this definite integral if I don't have an antiderivative formula? Well, this problem actually makes use of property number 1, where I can split it up into 2 separate integrals using some x value in the middle. Well, if you remember with absolute value functions, they're really just piecewise functions, where the rule changes depending on what your x value is. As long as the value inside the absolute value is positive, then the absolute value doesn't do anything. But if the value inside the absolute value becomes negative, then that absolute value is going to change the negative number into a positive number. So where does my rule change? What's this critical value where that absolute value is either going to change it positive or keep it positive? Well, I can answer that by just asking myself the question, where will this equal 0? And it turns out this will equal 0 at x equals 4. That represents this critical value where the rule changes. So let's look on either side. If I look at numbers bigger than 4, or actually numbers greater than or equal to 4, because this is true for x equals 4 as well. For numbers bigger than 4, what happens? If I plug in a number bigger than 4, like 5 or 10, 5 minus 4, 10 minus 4, those are giving me positive values. So does the absolute value do anything? It doesn't. You just end up getting the same exact value as if the absolute value wasn't there. But what about numbers less than 4? Well, in that case, the absolute value changes those negative numbers into positive numbers. Mathematically, to do that, I can just multiply everything by a negative. And that's going to change my negative numbers into positive numbers. So this is what the absolute value function is actually doing. And so what I can do is I can use that to split this up into 2 different integrals. My first integral, I want to just go from 0 to 4. Why 4? Because once again, 4 is that critical value where the rule changes. And then my second integral, from 4 to 6. Why 6? Because that was my original upper bound. Now, why did I do this? Well, let's start with the second definite integral. Since the bounds for this integral are from 4 to 6, this definite integral falls completely within this region right here, where x is greater than or equal to 4. Meaning that this absolute value of x minus 4, I don't need the absolute value anymore. I can just change it to just x minus 4. And now I don't have to worry about taking the antiderivative of an absolute value. Well, if I go back to the first function, this one, because my bounds are from 0 to 4, this one falls completely within that first region. And if I'm in that first region, then the absolute value turns the number positive. It takes your output and makes it positive by multiplying by a -1. And so I can rewrite this as the integral from 0 to 4 of x minus 4 multiplied by a negative, or by -1. And so by using that rule, I once again was able to get rid of the absolute value. And now I can move that negative outside because it counts as a constant multiple, and I can now find the integrals of both of these functions because the absolute value is gone. What's my antiderivative of x minus 4? I get 1/2 x squared minus 4x, evaluated from 0 to 4. And then for the second integral, it's the same function, so I'm just going to get the same exact thing. 1/2 x squared minus 4x, evaluated from, but in this case, this one's evaluated from 4 to 6. Then I can plug in my values. So over here I get, when I plug in 4, I get 1/2 4 squared minus 4 times 4. Minus, wait, what happens when I plug in 0? If I plug in 0 into both of these terms, I just get 0 for both of them. So I don't need to worry about plugging in 0 into this because I just get 0 when I plug it in. Plus, now I'm going to do my other one. So I get 1/2 6 squared minus 4 times 6 minus 1/2 4 squared minus 4 times 4. Now I can evaluate this while I distribute these negatives, and I get -8 plus 16 plus 18 minus 24 minus 8 plus 16, which is equal to 10. And there's my answer. So once again, the key to this one is using that first property to split it up into two different integrals, separated at that critical value where the rule changes with my absolute value. Another way to think about this is really just the area of the function x minus 4 from 0 to 6, but I'm counting both of these areas as positive, because what the absolute value does is it makes it bounce off the x-axis and go back to being positive. That's what the absolute value does. So that's really all I'm doing here, is I'm taking the area of both of these sections, but counting that first area positive when normally it would be counted as negative. Okay, let's look at the next problem. This one's actually number 5 from your homework. This one wants you to find the area bounded by these two graphs, the region bounded by these two graphs. And you may already be able to guess, this uses the second property, right? Since I have two different functions, I'm probably finding the area between these two functions. And that's exactly what this one's asking. But there's two kind of hang-ups that we have here before we can actually write my integral. First of all, which one's the bigger function? Well, in order for me to be able to answer that, I need to know which interval I'm looking at. And that leads me to my second problem. This doesn't give me an interval. It doesn't give me a lower bound and an upper bound, a starting point and an ending point. So what are my bounds for my integral? Well, the reason why this doesn't give me bounds is because these functions actually cross. They intersect. So if you have this function x squared, and then the function x plus 6, it looks something like this. And notice, it crosses in two places. So what this function's really asking for, or what this problem's really asking for, is the area of this region. This enclosed region that's created when you graph these two functions on the same page. So the first thing I need to do is I need to figure out what are these x values, because that will give me what my a and b are, if I can figure out what those x values are. How do I figure that out? I can figure that out by just setting these equations equal to each other. That'll give me where the functions actually intersect. To solve this, since I'm working with an x squared function, I'm going to subtract both of these over onto the same side, and then I'm going to factor. When I factor this, I get x minus 3 times x plus 2. You can double check my work by multiplying it back out. And what that gives me is two different factors that if either of them equal to 0, then it counts as a solution. So I get x equals 3 or x equals negative 2. And notice how that matches with my rough sketch that I have. Negative 2 is going to be this first x value, and 3 is going to be my second x value. And those now become my bounds. I'm going between negative 2 and 3. So that takes care of one of my issues. I now have bounds. What about my other issue? Which function is bigger, x squared or x plus 6? We might automatically think, oh, x squared is bigger because it has a squared exponent. But remember, we're only looking at a specific interval, and we're asking ourselves the question, which function is bigger inside this interval? So if you look at my actual picture, you can actually see that x plus 6 ends up being my bigger function. But if you can't visualize this, or if you have a hard time drawing the graph yourself, I can actually check this by plugging in a number that's inside of my interval. What's inside negative 2 to 3? Well, I can pick the number 0, and if I plug that into both my functions, I get 6 for my first function and 0 for my second function. That means this is your bigger function, and this is your smaller function for this specific interval. So that means to find the area between the two graphs, I'm going to do the definite integral of x plus 6 minus x squared. Since this is just a polynomial, I'm ready to go ahead and find my antiderivative using the fundamental theorem of calculus. So I get 1/2 x squared plus 6x minus 1/3 x cubed, and that's evaluated from negative 2 to 3. So I'll plug in my upper bound, and then I'll plug in my lower bound. Now that I've evaluated, I'll go ahead and distribute this negative to all three of these terms. And then I can start combining some. Since these are all constants at this point, I can go ahead and start combining things. So I get 9/2 plus 9 minus 2 plus 12 minus 8/3. Then I get 19 plus 11/6. 19 from 9 minus 2 plus 12. And I got the 11/6 from combining my two fractions. But that's my area between my two curves. Okay, the last question I want to go over is number 11. And there's a lot going on. This one has multiple parts. But I want to focus on part C. So you'll notice that's the one that I stopped on because that's the one that we're going to work through together. But I will talk about each of these first parts. Here we have a memory experiment with two subjects, Alice and Ben. And for each of them, we are given the rate at which they are learning new words. And so the first question is, who has the higher rate of memorization? And you'll notice that I've already answered this. And you might be wondering, well, how did I know that? Did I use calculus? Did I use some math? No, I didn't really. Take a close look at their equations. Here's Alice, here's Ben. Both of them share this positive 0.2t. Both of them share that. That's the same for both of them. So the only difference is this second piece. Both of those pieces are quadratic. They both have a t squared term. Both of them are negative, which means since it's negative, those pieces are counting against their rate, right? It's making the rate at which they learn words smaller because it's negative. So if you look at this, Ben has the bigger number. His coefficient is 0.015, and that's bigger than this coefficient of 0.003. So therefore, this negative value is counting against Ben more than this negative value is counting against Alice, and that's why Alice has the higher rate of memorization. Well, now that we know that, part B asks, how many more words does that person memorize during the first 10 minutes of the experiment? So 0 to 10. What is that going to be? That's property number 2. That's asking you to find this antiderivative from 0 to 10 of who had the bigger function? Alice had the bigger function, so we're going to do negative 0.003t squared plus 0.2t minus Ben's function. And if you're looking at that thinking, oh, that's going to be terrible, no, it actually simplifies pretty good because those terms actually cancel. But that's what part B is asking. If you remember, because these are both rate functions, then the area under the curve gives you the total amount of words. So now let's go to part C. Over the first 10 minutes of the experiment, on average, how many words per minute did Alice memorize? And this is the reason why I want to talk about part C is because this uses property number 3. Now we're finding an average value. But because we don't have specific data values or a finite number of data values, all we have is an equation. I have to use calculus. I have to use a definite integral. So in this case, my bounds are from 0 to 10, and I'm integrating my function, and once again, specifically Alice. So I'm going to integrate Alice's function. What that'll do is that'll give me the total amount of words that she memorizes over these 10 minutes. And if I want to know the average amount of words that she's memorizing each minute, I'm going to divide this by 10. You can also think that as your 1 over b minus a. Well, 1 over b minus a in our case is just 1 over 10 minus 0, which is just 1 over 10. And that's how I'm going to do this one. So I can go ahead and find my antiderivative of this problem. So I get negative 0.003 t cubed over 3 plus 0.2 t squared over 2. And that's evaluated from 0 to 10. This actually simplifies pretty nicely, and I get negative 0.001 t cubed plus 0.1 t squared, evaluated from 0 to 10. Go ahead and plug in 10, and then I can plug in 0. But once again, what's going to happen when I plug in 0? What's 0 cubed? It's still 0. What's 0 squared? Still 0. So when you plug in 0, that lower bound ends up just being 0. So I really only have to focus on my upper bound. I get 1/10 is equal to 10 cubed is 1,000. 1,000 times 0.001, that moves the decimal place 3 times, and I'm back to just negative 1. Well, over here, 0.1 times 10 squared is 100. 100 times 0.1 just moves the decimal 1 place, and so I get 1/10 times negative 1 plus 10, so I get 9/10. 9/10 what? That's the words per minute, the average words per minute that Alice is memorizing at. She's averaging almost a word per minute. And that's property 3 in action. So now you've seen all three of the properties in a specific example, and hopefully you can tackle the rest of them on your own. But if you still have questions, of course, please reach out, send me an email, and I'd be happy to help. Good luck, everyone.